Mr. Baina here, and welcome to Concept Map Lessons. And in today's episode, our topic will be about chirality. So, what is chirality? Chirality is actually a Greek word, or chiral is a Greek word. It simply means hand. And chirality is associated in chemistry as molecule handedness. This is an example of chirality. These are two compounds that are associated with handedness. One molecule here is a right-handed molecule, and the other is a left-handed molecule. Chirality forms or represents the left-handed molecule, and these left-handed molecules are usually the amino acids. Look at the compound. This is an amino acid. Look at the amino group in this compound. It is situated in the left side of the chiral molecule. While an example of a right-handed molecule is the naturally occurring monosaccharides. These are sugar molecules. Look at the CO groups of the different monosaccharide compounds. They are all found at the right hand of the molecular structure. The left hand and the right hand are actually the reflection image of each other. Or we can just simply say they are mirror image of each other. Although mirror images, they can be superimposable, such as the bottle of wine. No matter how you rotate the image or the object, they will have the same image and they can be superimposed. In other words, they can be aligned. This is also very similar to molecular structures. There are molecular structures that no matter how you rotate, they can be superimposed. And yet, there are two different structures but has the same mirror image. This type of structure is called a chiral object. Achirals are superimposables. Again, superimposable images are also known as achiral. They are superimposable because from their plane of symmetry, when you rotate the object, they are just simply similar and can be superimposed. Another type of mirror image is a non-superimposable image. An example to this is the two hands. They are both a reflection to each other's images, but they cannot be superimposed. There are also similar molecular structures that are similar to our right hand and our left hand. And this type of images or structure is called chiral objects. Chiral objects or molecular structures cannot be superimposed, no matter how you rotate the molecular structure. So again, when we speak of non-superimposable objects, they are called chiral molecules. These non-superimposable molecular structures are also called stereoisomers. Now, what are stereoisomers? Before we proceed to stereoisomers, we have to understand what isomers are. Isomers are those molecular structures that has the same molecular formula. However, because of the arrangement of the molecular structures, they produce different compounds. There are several types of isomers, and stereoisomer is just one of them. So now, what is a stereoisomer? Stereoisomers are molecular structures with the same composition, but they differ in their orientation of those compositions in space. So again, stereoisomer is just part of the general isomers. Now, since stereoisomers are mirror images but cannot be superimposed, they contain chiral centers. So what is a chiral center? In this illustration, these are the chiral centers. Chiral centers are actually connected to all four of the valence electrons of the carbon. The other one is also connected to all four of the valence electrons of the carbon. This one is a chiral center because they are all connected to all four of the valence electron of the carbon. This is also another chiral center, but this one is not a chiral center because it is not connected to all four of the valence electrons of the carbon molecule. A chiral center is a tetrahedral atom. Tetrahedral meaning 4. An example to this is carbon, meaning to say that this carbon molecule is bearing or holding 4 different ions or a molecule. Another name for a chiral center is called Stereocenter. Again, stereocenters or chiral centers are basically those carbon atoms that are connected to 3 or more other atoms aside from carbon, or maybe another group. Stereoisomers can be drawn with the Fischer's projection. This is developed or devised by Emil Fischer in 1891. This is Emil Fischer. So what is the Fischer's projection? Fischer's projection is this is a two-dimensional representation of a three-dimensional organic molecule by projection. The components of a Fischer's projection are the following. We have the intersection. This represents the chiral center. It also has a horizontal line. This horizontal line actually represents the molecules that are directed towards the viewer. And finally, the vertical line. The vertical line basically are those molecules that are moving away from the viewer or directed towards the screen or towards the page. In order to understand all these components of a Fischer's projection, the next page will illustrate to you how this is done. So the image on the right is basically the wedge type of model of representing a molecular structure. These are the wedge going towards the viewer, and these are the wedge going away from the viewer. So how is this being converted into a Fischer's projection? CH3 is moving away from the viewer, meaning CH3 is going into the screen. So they will be drawn into a vertical line. So all of the CH3s are moving away from the viewer. That's why they are represented in the Fischer's projection in a vertical line. While H and Cl, H and Br, OH and CH2CH3 are moving or oriented towards the viewer, so they will be represented with a horizontal line. And of course, the center is actually our chiral center, and so they are represented by the intersection in that Fischer's projection. There are two types of stereoisomers. The first type is enantiomers. Stereoisomers are chiral molecules. Thus, enantiomer is a chiral molecule. They are non-superimposable images. There are two types of enantiomer molecules. These are the L-enantiomer, or the OH is found on the left side of the molecular structure. L stands for left or levorotatory, that is left-oriented rotation. The other type of enantiomer is called the D-enantiomer. The D-enantiomer simply means dextrorotatory or right side orientation. This is how we got the name of dextrose, because most of the monosaccharides are right-handed molecules. Now, how do we identify the L or the D enantiomer? The D or the L enantiomer can be identified by looking at the second to the last carbon of the structure, or simply determining the OH from the CHO. This is the last OH from the CHO, or actually the second to the last OH of this molecular structure. Now in this case, the dextrorotatory glucose is located in the right side. So this is a right-handed molecule, while the L-glucose or levorotatory molecule is that the OH is towards the left. So again, this is the reason why we use the word dextrose. It comes from the word dextrorotatory, and this is a glucose. Now the next type of stereoisomer is a diastereomer. Diastereomers are not mirror images. An example to this are alkenes. There are two orientation types of alkenes. One is cis, meaning same side, and the other one is trans, or opposite side. Look at the Cl of the cis orientation. They are both in the same side. But the Cl in the trans orientation, they are in the opposite side. Diastereomers are like enantiomers. They are also chiral molecules, meaning they have also chiral centers. Diastereomers have different chiral centers. Because of this, it can produce different molecular structure combinations, or many possible combinations. And this can be determined by the formula 2 raised to the power of n, where n is the number of chiral centers. A diastereomer that has more than one chiral center is called an isomer. D-glucose and D-galactose are both isomers. Look at the two OH. Although the other OH is oriented to the other side, but there are two OH in here, and there is another OH in there. So meaning to say, they have several chiral centers. But these two are already regular, and one more OH that is added to this molecular structure is what makes it isomer. And that's all for chirality. Thank you very much for watching.